Excellent. Okay, good evening. I'm Nick Husser, and today I'll be presenting my Webb Institute senior thesis in investigation of turbulence simulation on 3D printed model propellers, and I was advised by Professor Adrian Onis. Before I begin, I'd like to first thank Professor Jack Hadler for giving me the idea for this thesis, and then Professor Adrian Onis for guiding me through the process. So this is a brief outline of what I will go through today. I'm going to have to go quickly, so I'm not going to spell it out for you. The objectives. I had two objectives in my work. The first was to study the effects of 3D printed plastic materials on model propeller test results in open water. So essentially, what is the difference between a metallic propeller result and a 3D printed propeller result? Second is to determine the feasibility of implementing turbulence stimulators at the leading edge of these propellers so that I can test them at lower Reynolds numbers. And I'll explain to you now why I wanted to do that. So in past testing at Webb Institute, started by Professor Hadler between 2015 and 2016, he began the first tests of 3D printed propellers. He used the Van Agenen B series, which is a recognized series out of the Netherlands ship model basin. There's lots of empirical data published on this series, and there are actually regression equations based on the geometry of the propeller giving its expected performance, and this would be for a metallic propeller. His goal was to study the effects of the test Reynolds number on the propeller results. However, while testing at the ITTC, the International Towing Tank Convention, test conditions, he had a blade failure, so he broke a blade off due to high loads. At his lower loads, before he fractured the blade, he had some unexpected test results that had not quite been explained. To mitigate his blade failure, he actually applied HAMA strips to the leading edge of the propeller, which that propeller is shown in the figure on the left. You may be able to make out the HAMA triangles shown here. And this is where I picked up the thesis and continued the work. So now I'd like to go into some of the background and the theory of my work, discussing 3D printing, expected Reynolds scales effects, and the theory behind turbulence simulation. So 3D printing is ideal for the manufacture of model propellers for three reasons. First, you can get comparable accuracy to the production of a metallic propeller for significantly faster and for less cost. So you can test more, you can test faster, and you get the same accuracy out of it. And in this thesis, I used the ProJet 3500 HD 3D printer that we have at Webb Institute to print my propellers. The big issue that arises using 3D printed materials, specifically plastic in this case, is that it's weaker and more flexible than the metallic material that the typical model propellers are constructed from. This results in propeller blade bending. And if you look at the figure on the right, the blue outline is a typical propeller section. If you can't see in the back, please feel free to come a little bit closer to the screen. The blue outline is a typical propeller section with the thrust and the torque shown forward of the mid-chord line. Therefore, this thrust of the torque on the propeller will create a bending moment that will result in an increased pitch of the propeller theoretically. And the higher the load gets, the larger this increase in pitch will become. This will theoretically result in an increase in thrust, non-dimensionalized as KT, or the thrust coefficient, and the torque KQ, non-dimensionalized as the torque coefficient KQ. Using first principles, I arrived at the equation that KT and KQ, the effects from just blade bending, should be proportional to the Reynolds number squared. I'd be happy to do that math for you later, but I do not have that much time. Next, we'll talk about Reynolds scale effects. Reynolds scale effects derive from the fact that there's a boundary layer in any viscous fluid flow, shown in the figure on the right. And in any boundary layer, there are two types of flow. There's a laminar region, which this laminar region is steady, can be well predicted, and the fluid particle follows a predicted path. Followed by a turbulent region after some distance along the plate, where the flow becomes unsteady, the particle moves in a random way, and this increases the frictional drag on the plate. Now, where this comes into effect in model testing is at the model scale, turbulence occurs where the red line is shown. This is all nominal. However, at full scale, when the speeds become faster and the Reynolds numbers become higher, that turbulence point shifts forward, closer to the leading edge. And since I said before that in a turbulent region there's a higher amount of frictional drag, the frictional drag between the model and the full-scale propeller will not be the same. The effect on this on the propeller performance then, published in Dieters in 2006, is that as the test Reynolds number is decreased, this is a constant propeller, this is not between model and full scale, the thrust coefficient will decrease and the torque coefficient will increase. I'm going to remind you of all this later, so it's going to be okay. Turbulence simulation. In ship model testing, per the ITTC, it's common to apply a turbulence simulator to the bow of the model to mitigate the Reynolds numbers effects that I just spoke about. This is shown in the figure on the left with Hama strips. These can be done with wires, studs, sand strips, or Hama strips. However, in 1956, Professor Hama performed a study in an attempt to quantify which of these turbulence simulators provided the best stimulation for the lowest amount of added drag, and came to actually inventing these Hama strips as a better method than any previous used method. And it forces the turbulence where it would occur at full scale. The parasitic drag and the turbulence simulation should, in theory, reduce KT and increase KQ compared to a model where turbulence simulation was not applied. To discuss briefly how these Hama strips work, here's a diagram. The first, the small dashed lines are streamlines close to the surface within the triangle. And you can see these streamlines converging towards this point and then creating a stagnation point. Slightly above, in the larger dashed lines, there is some contraction, but not nearly as much, and far away from the surface, the flow is unaffected. This changing in the amount of contraction creates a three-dimensional vortice, and that will actually produce turbulence behind the Hama strip. Now that we've gone through the basic theory, I'd like to talk about my procedure. First, the propeller selection, followed by the Hama strip design and how they're implemented on my propeller, an open water test procedure, and finally the test matrix that I tested in this work. So my propeller selection. As Professor Hadler did, I've continued to use a Van Agheneggen B-series, and this is because of those regression curves giving me a comparison point between a 3D printed propeller and a metallic propeller. Since Professor Hadler broke a blade, and I was able to, the load at which that blade broke was known. So I took that load and I reduced it by 25%, and I selected a propeller geometry that would not exceed that load during my testing in hopes that I could keep my propellers without breaking them so I could test them later if necessary. From that, I arrived at the following geometry. A 4-bladed propeller, 8 inches in diameter, which is limited by the size of the tray in the 3D printer, as well as the size of the tank at Webb Institute, a pitch to diameter ratio of 0.8, and a blade to area ratio of 0.525. I printed 2 of these propellers, one without Hama strips, typical naked, which I'll call a naked propeller, and one with the Hama strips, which I'll call a stimulated propeller. When designing a Hama strip, you must, in order to simulate turbulence, you must keep what's called the roughness Reynolds number above 45. The roughness Reynolds number is described by the equation above with the variables defined in the figure below. What's important here is to know what U sub K is, which is the height at the top, or the velocity of the fluid at the top of the Hama strip. So I need to know what this velocity profile is. There wasn't a lot of data published allowing me to predict the actual boundary layer of the propeller, so I approximated it in my design using a Blasius laminar boundary layer. Second, I needed to keep the height of my simulator inside the boundary layer. So if my simulator is all the way up here, all I'm doing is adding drag, and those vortices will not form that I discussed earlier. So to predict that height, I used an airfoil testing book done by Pope in 1984, which gave this equation used to size stimulators in airfoil testing for the height of the boundary layer del. My last limitation was my stimulator height. The 3D printer at Webb Institute had a minimum resolution of 2.5 thousandths of an inch. So I had to make my simulator height at least 2.5 thousandths of an inch to ensure accurate printing. This resulted, with many other factors that I don't have, again, I'm sorry I don't have time to discuss, in the design shown on the left. With a height of 2.5 thousandths of an inch, I wanted to keep the height as low as possible to minimize the induced parasitic drag. As well, I made the triangles point directly into the streamline, which I assumed was along a line of constant radius at any point. That is the major difference between my Hamas strip design and Professor Hadler's design that he tested originally. Notice also a larger spacing between the triangles close to the hub compared to the tip. The larger the spacing between the triangles, the stronger the vortice that they create, and this stronger vortice will ensure that turbulence is stimulated. So in the hopes of ensuring turbulence stimulation, I increased this distance here. The stimulators I also designed to only stimulate at 300 RPM and above, where I tested in this thesis between 100 RPM and 1100. Therefore, I would have some data where only the parasitic drag would be included in the test results, and allowing me to make a comparison and hopefully determine if turbulence was stimulated or not. As I mentioned before, I did open water tests on the propellers in this thesis, which is keeping the propeller in an undisturbed flow. So the propeller boat shown below moves with an advanced speed here in this direction, meaning the propeller is in front of the boat, so the flow has not been disturbed by anything as it would be in an actual ship application with the hull in front creating wake effects. To mitigate the Reynolds number effects without turbulence simulation, the ITTC recommends that all open water tests be run at Reynolds numbers above 5 × 10⁵, at a constant RPM and for a range of advanced speeds. This is the typical procedure. When you do an open water test, you first have to do a pre-calibration on your instruments. Calibrate thrust and torque. Thrust is calibrated dynamically with the shaft rotated at 100 RPM. This removes any friction from the journal bearings in the shaft and actually allows for a significantly better calibration. After the pre-calibration, no loads are performed with a dummy hub installed on the shaft, so a propeller hub with no blades. And this is run at the same conditions tested during the open water test, and then subtracted off of the final test results to remove the hub effects and only measure the effects of the propeller itself. During testing, you set the forward speed of advance and the RPM of the propeller, which is non-dimensionalized as J, or the advance ratio shown here. Note from the Reynolds number equation below, and the V0 equation specifically, that the RPM of the propeller has a much more significant effect on the actual Reynolds number than the J value. During a test, we then measured the thrust and the torque the thrust generated and the torque required to turn the propeller, and non-dimensionalized those as KT and KQ that I presented before by these equations. It's not significantly important to know what those equations are, except that a higher KT means that a higher thrust is produced comparatively. Finally, a post-calibration is performed after testing in the same manner as the pre-calibration. Presented above is the test matrix that I tested throughout this thesis, with advance ratio at the top and RPM to the left. The numbers inside of the table indicate the number of tests performed at each condition, and this test matrix was performed on both propellers. So this is just for one propeller. So there were 3 tests at 100 RPM and J equals 0.2 for the naked propeller, and 3 more tests for the Hummer propeller. There are 2 comparisons that this allows me to make. First is the typical procedure, constant RPM, shown by these red boxes. And the second allows me to compare the Reynolds number, or the RPM, at 3 constant advance ratios, 0.2, 0.5, and 0.8. All right, now I'm going to get into results. If I lost you, I'm going to bring you back right now. Here's what's important, what you need to remember. From blade bending, I predicted that KT and KQ will increase with Reynolds number squared for the same propeller. So as I increase the Reynolds number, as I increase the Reynolds number squared, I expect KT and KQ to increase. Second, from Reynolds number's effects on the same prop, as I decrease the Reynolds number, I expect the thrust coefficient to decrease and the torque coefficient to increase. Finally, between the naked propeller and the stimulated propeller, I expect the stimulated propeller to have a lower KT and a higher KQ relative to that naked propeller. So some test results. The graph shown above is the naked propeller test performed at ITTC conditions. So this would be a typical open water procedure, and this allows me to compare the 3D printed effects with the metallic to a metallic propeller. The J value, or the advanced ratio, is presented on the x-axis, and each non-dimensional coefficient, KT, KQ, and eta naught, are on the y-axis. The first thing to note is relative to blade bending. I expected KT and KQ to increase at higher loads as a result of this blade bending, and you can see that here by this box. There's something questionable about these results, however, in that the zero values for KT and KQ in my test results occur at a lower J value than they do from the regression. I haven't entirely worked out why this has happened yet. I'm going to first verify that the propeller I printed is actually a B-series propeller one more time, and then see if there are any geometry differences there that could explain the differences. Also note, as a result of this, that there's an efficiency drop-off earlier than in the regression, which a higher efficiency at low J values and an earlier efficiency drop-off is consistent with a lower pitch to diameter ratio. So with a lower pitch to diameter ratio propeller, so that geometry also needs to be confirmed. I could show you the other 5 tests that I have for these RPMs, but that wouldn't be very useful. So instead, to quantify the accuracy of each test, I calculated the area between my tested curve and the regression curve, and I presented that in the following figure. The following figure has RPM on the x-axis and area between the curves on the y-axis. This is the absolute value of the area, not simply the integral, as the integral would allow positives and negatives to cancel out. The orange shows a naked propeller, and the gray shows a stimulated propeller, with the dashed lines being the torque coefficient and the solid lines being the thrust coefficient. Notice here, at an RPM around 1,000, the HAMA propeller begins to agree with the test results at lower Reynolds numbers, or RPMs, better than the unstimulated propeller, which would be an expected result if turbulence was in fact stimulated. All right, the next graph I'm going to put up is complicated. Just pay attention to me. I'm going to walk you through it. Don't try to examine the whole thing at once, or you'll get lost. So, this graph shows Reynolds number on the x-axis and thrust coefficient on the y-axis for J values of 0.2, 0.5, and 0.8. So the constant J values that I measured in my test matrix, with the diamonds showing the HAMA propeller and the circles showing the naked propeller. Okay? First, we're going to look at blade bending once again. At J equals 0.2, which is where the highest load occurs, you can clearly see that there's an increase in the thrust coefficient at high Reynolds numbers, proportional to the Reynolds number squared. At J equals 0.5, it becomes slightly less, which is expected because it's a slightly lower load. And at J equals 0.8, you almost can't see it at all, which is consistent with bending once again because there's very little load on the propeller. Now, I've overlaid a squared regression across just the naked propeller results to show the Reynolds numbers as trends. As predicted, I expected that at low Reynolds numbers, the thrust coefficient to be less than it is at high Reynolds numbers. This is shown at these low Reynolds numbers relative to the highest Reynolds number tested, and is consistent across both the HAMA propeller and the naked propeller. The same graph now is presented with the torque coefficient on the y-axis instead of the thrust coefficient. Again, you can see the bending effects, and you can see the Reynolds numbers effects, except in the case of torque coefficient, I expected an increase at low Reynolds numbers instead of a decrease, shown here. Also note, especially as can be seen on this torque coefficient, these solid lines are the SMPE regression values. At J equals 0.5 particularly, the HAMA propeller has an excellent agreement with the SMPE regression, while at low Reynolds numbers, the naked propeller diverges at all points. I then had to do an uncertainty analysis since I tested at 3 conditions for most things. Don't worry about the numbers, not important. I'm going to show you a graph. But the only thing that I want you to see here is that at 100 RPM, the uncertainty at all J values for both KT and KQ is significantly higher than it is for all other values tested. And when you look at the following plot for KQ with the error bars included, it's clear to see that at the lower values of RPM, where the loads were lower, the uncertainty climbed dramatically. So some conclusions. Can clearly see the bending effects as predicted at high loads. The effects of the Reynolds number on the naked propeller were also as predicted as the Reynolds number was decreased. Third, the Webb Institute propeller boat was inadequate for testing below 300 RPM, and to decrease the Reynolds numbers to the range where I wanted, I should have used a cavitation tunnel, but none was available. Third, the stimulated propeller produced a higher KT and KQ than the naked propeller at all test, well, not all test conditions, but at high Reynolds numbers where the accuracy was high enough to be confident in the test results. And relative to Professor Hather's results on his propeller, my difference between the two was less, which indicates that the change in the stimulator design actually improved the test results and the efficiency of and the accuracy of the test result. Lastly, the deviation between the SMPE regression and the stimulated propeller results was less than the deviation between the regression and the naked propeller results, which I cannot conclusively say that that was because turbulence was stimulated, but I can say that I got better test results from the Hama propeller than the naked propeller, and I'm still working on proving that turbulence was stimulated. I can prove this through a correction methodology that I need to develop for both blade bending and the Reynolds number effects. So in my continued work, I plan to 3D scan the two propellers that I tested to compare the geometry of each to make sure I was comparing apples to apples. I plan to verify that the propeller I tested was in fact the B-series geometry. I believe that it was, but I'm going to double check. And I need to develop a correction methodology for the stimulator drag and the blade bending. Thank you, everyone, and do you have any questions? Yes, sir.
I have a comment and a question. Comment on your Reynolds, on the stimulation, having the results being better, matching
They stimulated better than the naked.
Yeah, better than the naked, matching your regress. It seems reasonable because that was a correction that on the Wageningen propellers along their history where they recognized the Reynolds number situation.
Yes, and they were also tested at a higher Reynolds number than I could achieve in the tank because they were testing larger propellers.
Okay, but it seems in the right direction. And then the question is, you mentioned the ITTC. You've investigated this printing of propellers. Is the ITTC addressed this issue more recently?
I have not seen any papers published on testing 3D printed propellers. It's possible that I missed it at some point in my research, but I did not personally see it. Anybody else? Excellent. Thank you very much.